Analog and digital signals have to be converted from one form or another to make them more suitable for processing or consumption. First, let's take a look at how an analog signal is converted to a digital signal. I shall demonstrate an analog signal by turning one of the sides on this Rubik's cube. Suppose we would like to digitize the act of turning the cube once, like so. This is the signal we are going to digitize. To digitize an analog signal, we need to observe the immediate state of the analog signal and note it down at regular intervals. We keep taking notes until we are satisfied with the data we have captured. This is known as sampling, and the rate at which we take notes is known as the sampling frequency. I shall now demonstrate the process of sampling. Suppose a sampling rate of 1 Hz. That is to say, we will take notes at the rate of once a second. And this is the analog signal we would like to digitize. So here we go. Sample, 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 sample. The analog signal has now been digitized, and we have 4 samples of that analog signal. Now, observe the characteristics of the digitized signal. The original analog signal was a smooth turn of the cube. However, our digitized signal looks something like this. This is because we only have 4 samples of the original analog signal because we were sampling at a rate of 1 Hz. In other words, we were digitizing an analog signal with very low resolution. Recall that an analog signal has an infinite number of possible states. Suppose we are going to digitize our analog signal again, but this time we are going to increase our sampling frequency of 1 Hz and bump it up to 2 Hz. This will effectively double our resolution, as I will now demonstrate. Again, we would like to digitize this signal. So here we go. Sample, 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 sample. With the increased sampling rate and thus more resolution, our now digitized analog signal looks like this. With the increased sampling rate and thus resolution, we were able to more accurately represent an analog signal in its digital form. The demonstration that you have just seen is the function of an analog to digital converter, or an ADC, or AD. Now, let's take a look at its polar opposite, a digital to analog converter. Let's go back to the part where we had digitized our analog signal. With this digital signal, we would now like to turn it into an analog signal so that we could have it output somewhere. For example, it could be driving a motor, or driving a speaker, or showing an image onto a screen. However, if we were to directly convert the digital signal into an analog signal, we would end up with a very jagged or harsh analog signal. Recall that a digital signal has a finite number of discrete steps. This digital signal has to be smoothened out, and this is done with the use of a reconstruction filter. A reconstruction filter works by removing the high-frequency artifacts that were generated as a byproduct of the sampling process. With the help of the reconstruction filter, our digital signal turned to an analog signal now looks something like this. And this is the process of a digital to analog converter, or a DAC, or DA.